Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. And this section, 07, we consider the cyclophotometry. In the previous section, we talked about the linear scan photometry. The potential was scanning from one direction linearly, increase or decrease. But in this section, we'll talk about is the potential still linear increase or decrease in the scanning the potential from one position to the other position, but also it will reverse back or scanning back. We call the cyclophotometry. So this one called the cyclophotometry, abbreviated as a CV. The CV in the previous section we talked about for the linear scanning photometry at a low scanning rate. At a low scanning rate, we measure the current against the potential. This is almost like a steady state, nearly steady state condition. But we scan it at a much faster radiation rate. Then we got a transient behavior this way. Now, it's not only the transient, but we're scanning the potential back and forth within a given region, rather than just scanning in one direction. Then we got this potential. And this one, the potential scanning is also a faster scanning rate. So it's a transient behavior. And this one we call the cyclophotometry, CV here. So for the CV, there's a different kind of attribute to the current we measure. The first is a double layer charge and discharge. So if you think of this is the electrode and this is the electrolyte. So when you apply voltage, they start charging the current. They start the charge at the electrode, and also there's a mirror image of the charge on the electrolyte also will be formed. And this one just like a capacitor. The capacitor, the current flows through the capacitor is equal to the potential difference here. So you had a more charge, you pump in charge, then the potential across the interface will be increase or decrease, like this. The proportional constant is a capacitor. So if you cyclic the electrode surface, the current is due to the double layer charging current, then you may end with a square current, like a square pattern like this. That means at a low scanning rate, you got going like this red. Is center at the current at 0. Because at the highest scanning rate, the current is bigger. So you increase the scanning rate from 0.01 to 0.05 or 0.1, then the current will be increased, something like that. This is due to the double layer charging. They always in the cyclophotometry always have this kind of behavior, always including double layer charging, discharge current. But magnitude sometimes small, sometimes a bit large, depends on what kind of electrochemical reaction you're talking about. So the next is a Faraday reaction, including the mass transfer electrochemical reaction will play into the play. And then the double layer charging discharge still exists, but the kind of decrease minimized, very small, is not significant. So we're scanning the potential from one location to E lambda, and then we end with this previous that we saw, the linear scan photometry. Now we're scanning at the lambda this time, then we're scanning back. Then we end up with this kind of behavior. So it's like a copy of this one, but a reverse condition here. This is a typical result for the vanadium redox reaction. There's a redox for the reaction 4 oxide to 5 and 5 to 4 reduce. And you can see the peak, the scanning back and forth, the cyclophotometry at a different concentrations of uric acid. So you can see the acidic of the solution will be affect the vanadium 4 and 5 reduction oxidation peak over here. Also the scanning rate will be affected for the vanadium 3+, 2+, the redox couple reaction. You can see this one we can use reversible reaction or irreversible depends on the reaction. Usually for 2 and 3, it's almost you can use reversible reaction. You can see the potential peak is a little bit close then compared to the 4 and 5 over here. So from their paper, they're able to assume this one for the irreversible reaction. So the equation, you can calculate reaction kinetics at a different pH value or the proton act concentration. The reaction rate constant will be different. You can see from here. But the diffusivity should be close, very close together within this vicinity. And the peak current ratio almost the same. But the rate constant significantly decreased. And this is another example for the redox flow battery and for the 4 to 5. And it is graphite electrode, and the reaction taking place at the graphite. Before the smooth graphite, the cyclophotometry show like this. But after you polish the graphite, make a roughness, make it more rough, the electrode surface increase, then the cyclophotometry behavior become much larger. And you can see the peak potential is much close compared to the before the treatment. So at the before, the graphite electrode is less active, so you may treat it as an irreversible reaction. But when you roughen up the electrode surface increase, you can sand the electrode by sandpaper. Then electrode surface increase. Then since it become more active, the peak current was increased, and then the difference between this peak potential are getting close.